All right, welcome everyone. So tonight we're going to be going over the Kimi K2 paper and product. Um, so with that, there ended up being quite a bit in here. There's some areas that were fairly straightforward, some areas that I'm still struggling a little bit with. So if anybody has got insight, feel free to interrupt and ask questions or correct me if I got it wrong. Um, okay, so Kimi K2 is the latest model released by what is it? Is it Moonshot? I think it's Moonshot.
Got a moonshot.
Yep. Um, Tonight we were going to go through then the Kimi K2. They call it the Open Agentic Intelligence. This is, I provided the link. Actually, let me switch over here to this. That gives you a little bit bigger view, right? Um, we're going to go through. They made a lot of the Muon optimizer, which was something I hadn't heard of before. And so I'm going to dive a little bit into that as well, pull it aside, a little bit about the architecture, a little bit about how training, and if we have enough time, we'll get to a demo at the end. Okay. So this was the abstract. There's just a couple things that drew my attention here. One, it's a trillion parameter model with 32 billion activated at any one time. The other part that was interesting is this multi-stage training, especially using this RL stage, I thought was interesting. So we wanted to kind of dive into that. Their claim is that they are surpassing the open source. We'll see in the results that they do well against the other open source. They're still lagging in most areas um, behind the closed source models, but they're doing well relative to the open source one. And then there's this little comment that they made that uh, what we're seeing here is not thinking models. This is just, I don't know what you call the non-reasoning models, but these are all non-reasoning models. So, okay. Um, the introduction, they make a point that this agentic intelligence, so the idea that these language models are interacting with agents becomes an important part of kind of the state of the art right now. And that's important because they really emphasize the agent interaction in their training process, in the post-training process. Um, and so that kind of caught my attention. Yeah, pre-training, post-training. They made the point that um, there is, this leads into one of their training steps, a limited amount of data in the um, that they can use for these types of agent interactions. Um, and what did they say? Post-training must transform priors into actionable behaviors, and yet agentic capabilities rare in natural data and costly to scale. So they're going to use actually synthesis of these agents. This is an area that I didn't fully kind of grok what they're doing, exactly how they're doing it, but we'll talk a little bit there. And if anybody has any ideas on what they're actually talking about there, that'll be helpful. Um, I thought this was an interesting statement that given the increasing limited availability of high quality human data, we posit that token efficiency is emerging as a critical coefficient in the scaling of large language models. So larger language models, you need more data. And what they're saying is we're actually getting to a point where um, uh, the being able to use those tokens efficiently becomes an important aspect of, I guess, the model or the training scenario. So they're going to be using synthetic data generation as a way to effectively increase that token efficiency. Okay. So here's where I dived in because they start out with Muon as an important part of it. They actually add something to Muon, but it seemed like there was a lot to the optimizer. So Muon is a um, uh, optimizer, much like Atom or something like that. Um, and it was introduced. Um, it was introduced interestingly in a blog post, as best I can tell, but as kind of setting the foundation for it. Problem with standard gradient descent is that this is the gradient descent. You're going to optimize the parameters by using some learning rate based on the gradient of the loss function with respect to those parameters. And we use the negatives because we're moving down to the point of lowest loss. This is standard. This is what everything. This is SGD. This is how it works. But one of the things that makes it difficult is that I'd never heard it phrased quite this way, but it's based on the assumption that the parameter space is flat or Euclidean. So it's looking at kind of treating all dimensions as equal, and that doesn't work. That isn't true necessarily in language models or in neural networks actually. Um, and this one I remember we had talked about some other optimization techniques using Fisher matrix and Kronecker decomposition, I think it was. This idea that the mental model that I have is that this in a long, narrow valley, if you have the loss function looks something like that. So just thinking in a couple dimensions here, that gradient descent typically looks at the direction that is downhill, or up, I guess, depending on how you look at it. But gradient descent would look downhill. And typically the downhill, if you think of yourself as on the side of the valley, the downhill is down towards the river at the bottom. And if you have, depending on how big of a step you take in that direction, you will overshoot and end up on the other side of the valley and then bounce back and forth. So that's this zigzag that they're talking about. And meanwhile, there's another direct dimension, which is downstream, and that's very flat. And so you're not, the downhill doesn't point very strongly in the downstream direction. So it takes you a long time to get downstream. You just keep kind of bouncing back and forth on the bottom of this valley. So that's the mental model that I have for the problem with gradient descent. Any questions on that? Okay. Atom, which I think is the most common optimizer right now, or at least for the last bit of time, last years, uses a mechanism that has two optimizations, momentum. So it essentially accumulates the gradient each time if they're going in the same direction, it's accumulating that gradient. So it kind of weights more heavily gradients that are always going in the same direction. So even though you're bouncing back and forth across this valley, downstream is always the same direction. So it starts picking up more and more update in that direction. You're not only going down, but towards the side. What was the question there? Yeah, right. So, there's a few. I missed a few. Ted, was there
Sorry,
anything?
there's a little bit of side chatter,
Yeah,
Roger.
was there anything to bring up on that?
No, nothing critical.
Okay.
Just me yammering about my favorite neural network again.
Oh, okay.
The way to use it.
Okay. And I think the RMS prop, so it uses the squared gradients, and I think that's an attempt at trying to get some of the second order effect. So Atom combines these two to try to narrow it out. There was another one that we talked about a while back, and this is probably a couple of years, where we talked about natural gradients. So there's one approach you can do is natural gradient. It's got to do with this Fisher information matrix, where you can essentially convert that by scaling the parameters or scaling the updates, kind of. You can take that valley and make it more into a bowl where the resulting vector is actually in the direction of the optimal downhill or the lowest point. And this again used the Fisher matrix. So it's much more efficient You don't get that back and forth bounce zigzagging. You can take bigger steps because it's always in the right direction, and it's much more efficient. But one of the problems is that in order to use this Fisher matrix, you have to compute um, this inverse of the Fisher matrix, and that's going to be the dimensionality of that is going to be the parameter space, size of the parameter space. So it's like a ridiculously large matrix and makes inversion virtually impossible. There's some approaches. Again, I think Kronecker decomposition, I think, was one of the ways to do it, to try to approximate that inverse. But that never really caught on, it seems like. And the atom was close enough. So this is a nice theoretical approach, but doesn't really work. There's a nice video if anybody's interested. Mutual Information is the podcast that goes over the information matrix and what that means and how it works.
Hey, Roger.
Yeah.
I say this as a joke, not serious, but try and figure out how many operations it takes to calculate the inverse of a since K2 is trillion parameters, of a 1 trillion by 1 trillion square matrix.
Yeah,
I think it's like n cubed.
Is it a cube function?
I think naive inverse is like cubed. So trillion is 10 to the 12th, so it'd be like 10 to the 36th operations to invert that.
Yeah.
Funny. No problem.
Yeah, I think that the thing that is apparently, they talked about this in the muon paper or blog, I guess, is that typically these matrices are very sparse. And so when you take that gradient, there's like a few of these dimensions that matter and most don't. And so, yeah, I'm trying to imagine what that, I guess, does that mean we're mostly valleys? I don't know. But yeah, that's the Kronecker block diagonal decomposition, I think, was the one that was taking advantage of that kind of sparsity. Okay, so muon, momentum orthogonalized by Newton-Schultz. So correct me if anybody knows differently, but from what I could find, this isn't like an archive paper. There's a blog post on it through this Keller Jordan, and I think from what I could see, he's actually the author of it. And there's other follow-on work, but it didn't show up anywhere else. He's got a blog post here. He's got which I think I brought up. This was the blog post, I think. And he also has a repository where he goes through that. So anyhow, it apparently, and again, I'm not sure, I think I'm going to have to dive into this more, but I'm not sure if it's like theoretically grounded or it was something that they do talk about it having the effect of orthogonalizing the gradient. So it's reminiscent to me of that, the natural gradient, that it's trying to make it so that all the dimensions are kind of treated equal. So you can take steps not that are equal in terms of their effect on the loss function as opposed to equal in the parameter space. This site here, this link provided, was starting, I just found this later, so I hadn't finished going through it, but it seemed like they might cover kind of what's the theory behind the muon and how and why it works. But again, I didn't really get it myself. Does anybody else have anything that can contribute there?
Sorry, what was the question?
Well, I'm just trying to understand muon and like what's its theoretical foundation.
Mm-hmm.
I hadn't found a good source for that other than maybe this Jeremy.
Um, let's see. I'm trying to think. Let me see if I have uh anything in my notes here. Mostly kind of where I don't have like the basically just the way like I have it formatted in my head is the like effectively like Atom is working like within 2D and then clipping there as opposed to Muon, which is rather than like squishing it down into a 2D shape, we can work with the full like 3D shape effectively. Is like not really foundationally or theoretically relevant. It's just like how my brain is categorizing the thing, basically. Um,
Well, so here's the equation that was in his original blog post. A little bit different than what they list in the Kimi paper, but we'll see that. Ted, you popped up. Did you have something to add there?
Well, I've been meaning to spend more time understanding muon, but I can give just like a little bit of background. Okay.
Okay.
So your valley analogy is good. It's the same intuition that I have. Okay. Um, if you in 3 dimensions have a perfectly straight valley, but the valley floor has some slope to it.
Right.
Okay. Then ideally what we'd want to do if you were human, you would just go down the slope until you got to the valley and you would walk along the valley floor, right? But if you're ever so slightly off the center of the valley floor, as you said, the gradient is actually pointing down to the slopes. It's not pointing along the valley along the fast direction. um, RMS prop, which is also built into Atom, I think Atom is basically RMS prop with momentum.
Right.
Okay, it will completely correct for that.
Okay.
So that's one of the reasons why we're using flow amp. So what they will do is they will scale all the dimensions um, differently. So if you imagine that the valley is running north south and that the slopes are all in the east west direction, okay, you're going to have a ginormous gradient in the east west direction and a very small one in the north south. But if it scales all of them to be one, then effectively what you're doing is you're decreasing the amount of movement east-west and you're increasing the amount of movement north-south, which is what you
Right.
want, right? You
Right.
want to move along the valley floor, which I've said is north-south. I think where the complexity comes in is that what if you don't have a perfectly straight valley floor? What if your valley floor is now curved a little bit or whatnot? So that means that you now have interactions between the north-south and the east-west.
Mm.
I think you're even okay if your valley's perfectly straight, but it's on a diagonal, right? Because that just basically means that you're
Yeah.
you're you're
Yeah. Yeah.
you're scaling things linearly, right? So like maybe it's 1/3 north south, 2/3 east west. That's fine.
Yep.
But as soon as you have a curved valley, now things don't work as great. Okay, so um, from what you just showed as a description, if you can do a spectral decomposition of the gradient. Okay, so if you find all the eigenvectors and the eigenvalues associated with that gradient, then uh, um, my linear algebra is not perfect, but like if you have unique eigenvalues, then the eigenvectors form a basis, and so basically you could just do a linear transformation into the eigenvector space. Okay.
Right.
Said another way, there's a matrix you can multiply that converts from your coordinates to the eigenspace
Projected.
or
Yeah.
from the eigenspace to your coordinates.
Yep. Yep.
If we said that an orthogonal space in which all the different the valley directions are not interacting and we have straight valleys, RMS prop works great, then all we have to do is do gradient descent in the eigenvector space instead of in our raw coordinates. But you don't have to actually literally move there. We said that there's a matrix that will convert from one basis to the other.
Right.
So if you just scale your updates by that matrix, if you multiply by that matrix, then voila, you've essentially done the equivalent of moving in this orthogonal, really well defined, independent directions space, but you're actually doing it in the regular. So then,
Yep.
of course, you could say, well, let's literally do this. And I believe that calculating the eigenvalues and eigenvectors is fully exactly is, again, one of those like super expensive things.
Right. Right.
It's between like n squared, n cubed, somewhere around there. So,
Yep. Yep.
so it's this Newton-Schultz thing being fast, I think, that allows us to do this and to do this reasonably quickly. Otherwise, we could do the natural gradient thing. You could also calculate all the second derivatives, and that basically tells you the interactions between. But the
So
second
yeah.
derivative of the Hessian matrix is
Right.
again one of those trillion by trillion matrices that's complicated to calculate. And so that's why all those other things are all theoretically great, but what we need is something that's good and also cheap.
Right. Right. And it looks like
So,
this, maybe this muon is getting closer to that, or moving in the right direction at least. So,
mhm.
so yeah, so that's interesting. So thinking about it's not always a straight valley. It has curves to it. The other thing you might that I might extend the analogy is I can imagine that a steep bottom valley is much more difficult than a rounded bottom valley because it's much more difficult to be near the bottom and see where the downstream is if I've got that very sharp valley as well. But
uh, I
I've
don't
got
think
to
it's
get
worth
close.
going. I don't think it's worth going down the rabbit hole. I think actually, uh, you're worse off the steeper it is, because then if you're ever so slightly off the center of the valley, it
Yeah,
looks like you're on a really steep slope. Whereas if it flattens out, then you can actually get an accurate reading. It looks flat in all directions, and you can get an accurate reading of which way the valley is
yeah,
actually. But
that's kind of
but we don't need to go into
yeah.
gory detail.
But anyhow, good mental model. Yeah, so what's going on here then, I think, is this basically is getting the gradient of the loss function with respect to the parameters. This is a momentum. It's basically running like a moving average, exponential moving average of the gradient. So that's what the B is. And then in here is where we do they call it the orthogonalizing the vector. So O is going to be an orthogonalized representation. And that's what we actually use um, the gradient uh, accumulation, the gradient descent on using that. So this is moving that into kind of that. I think I'm not quite sure. I don't remember the difference between an eigenvalue decomposition and an SVD composition, but I think this is an SVD composition of the gradient.
Yeah,
And
and the
that's
singular values are just the square roots of your eigenvalues.
okay.
And so it's sort of the same
Same thing.
concept. Yeah,
Yeah,
whether you have your U matrix or your eigenvectors, you're talking about, sort of a different basis.
great. Okay. Um, and then the kind of the important thing that shows up in the blog right away is these curves. So focusing over here, they got let's see, validation loss versus training tokens. Adam's the blue one. It's the one along the top here. Apparently, there's a couple other second order-ish of algorithms that they're comparing against. But move on. Was somebody saying something there?
Oh, I was just remarking on also shampoo, which is sort of in some of the ML group chats that I'm in. People were looking for alternatives to Atom for a while, and shampoo was sort of like the actual promising version of Muon before we saw Kimi like do Muon clip basically.
Gotcha. Okay. So yeah, and the muon is better. So lower validation loss for a given number of training tokens. Um, and it looks like they do another these you can see have different rates that they're doing updates. So some are Muon, I guess, is a little bit actually slower. Interesting. Soap is quite a bit slower. So anyhow, when you represent it based on time, then and loss, validation loss versus time, again, Muon shows up good. Soap, it looks like because it's run so slow, is not so good. Um, so anyhow, those are the curves that say, hey, this stuff works good. Um, why is it good to orthogonalize? I thought this was actually in the blog post, which I thought was kind of interesting. Is what's his name says that it just is, okay? Which I thought kind of very informal, was fun. But again, here in his blog, it sounds more like anecdotal, observational rather than theoretical, theoretically derived. So again, but I've seen other people say that it has a strong theoretical foundation. So I'm still a little bit confused on that. But the net effect is that that was the algorithm. Whoops. See, how do I go backwards?
Hey, Roger.
Yeah.
Um, I think what it's got to do is it's got to expand the gradient into the orthogonal vectors, and then get the proper scaling for each one, right? Because what you really want to do is divide by the Fisher information matrix, which is I think more fundamentally just the covariance matrix, the second derivative matrix, and so that turns the gradient descent into Newton descent, which converges quadratic. And the way I like to think about it is that it approximates the loss function by a paraboloid and then jumps to the bottom of it with one step of Newton's method, whereas gradient descent is just going downhill, downhill, downhill. And so, this sort of poor man's Newton's method is to just divide each dimension by the variance in that dimension. So it's like the curvature along that one axis. And so it's got to be doing something like that, where you take your gradient and you would like to transform to the other space, which is orthogonalized, which would be like dividing by the second derivative matrix, but you don't want to spend that, and so you just what you do instead is just expand the gradient into the eigendirections, and then apply the scaling for each one, and then add them back up, and that should give it. But I haven't read this. I'm actually looking for a paper. I'll post it when I find it, and if I can figure out what they're doing. But it's got to be something like that, right? I mean, I just wanted to throw out that terminology. I saw all this stuff back when I was doing system identification. So
Oh, really? Okay.
yeah, so we started out with the LMS algorithm, right? Bernie Widrow, and I think it was a spin-off of perceptron research from like, the 50s or whatever. And so in the 60s, it became the LMS algorithm. It got applied all over the place, and it was known for being able to design very, very large filters. In those days, that was like 256 taps, 256 weights. And we thought that was really big. I was amazed because, I was actually working on Newton's methods. They're called recursively squares, recursive Gauss-Newton. And the usual approximation for the inverse Hessian was the sum of the outer product of the gradient. That gives you sort of the first term. So you can expand it. There's this matrix inversion lemma that will express the inverse covariance matrix as the sum of outer products of gradient plus some other terms that are hopefully small enough and you neglect them, and it's guaranteed to be positive semi-definite, and it's got all these nice properties, and it's an order n squared operation. You can just, it's an outer product, order n squared outer product. And so that actually is what we used. But we weren't getting, 256 weights in real time. We were doing recursive filters. And so it was a lot more work. And we had smaller stuff, smaller filters. But that was the Newton method. And there's a ton of them. There's a huge literature in this area. I don't know, probably thousands of papers in this stuff. And if anybody's interested, I was a graduate student at that time, so I'm really, I really loaded up on that. I studied it intensively for 2 years, so I know quite a bit about it, or at least at one time I could refresh those memories. But basically, you're just trying to do that. And so then there was another variant called the stochastic approximation method, where instead of just approximating the inverse Hessian by the inverse covariance matrix by a sum of outer products, you would actually diagonalize that. Just ignore the cross correlation, and you at least get
Yeah.
the division in each dimension divide by the right variance, and it was like LMS with a custom scale factor on each dimension, and that did the straightening of the valley. So the steep sides of the valley have a high curvature, so you're going to divide by a large number and slow down the gradient. And in the long valley direction, you have a very small curvature, and so you divide by by a very small number, which really speeds it up. So you get the speed up, and it normalizes. I mean, it effectively, when you do it really right, it turns the long skinny valley into an actual bowl, and
Right.
and you really go right to the optimum solution in one step of Newton's method. Just really, the next iteration, you're there at the bottom of
Well,
the.
if it's actually paraboloid,
Right,
you
right.
can do it. Yeah, yeah,
So you're always hopping to the bottom of the locally parabolic approximation. So wherever you are on the loss landscape, you fit a paraboloid to that and jump to the bottom of it. And then, unfortunately, it was not a paraboloid, so you do it again, you do it again,
yeah,
so you know the story. So, so it's got to be doing something like that. And I'm gonna find the paper and send a link.
yeah.
I'm
Okay.
interested.
Well, it'd be fun, Julius. It'd be fun. Maybe sometime in the future here we could go through that the original Muon paper, and your insights might be very
Oh yeah.
helpful on understanding that. So
Yeah, I actually want to know this. I mean, it seems like an extension. It seems like a natural extension of all of the stuff that I learned way back when, and so
yeah,
I'm very curious.
and
Uh,
and somehow we it's an efficiency win too. So that's cool. And
yeah,
there's another dimension on this I didn't understand, and that is in some of the smaller examples that they provided, it was moderate improvements, but somehow it's related to the model size. Where in the case of Kimi, I read someplace, couldn't run back to cite it right now, but that it was essentially achieved the same level of loss um, in with a 75, so like only 25%, so like 4 times faster than an Atom algorithm would have done. So and that somehow again, it seems to be better for bigger models. I didn't have intuition why that would be the case, but good. It was good. It was a
yeah,
good
that's
fix.
the model size is the order of that covariance matrix, right? So
Yeah.
that's what you're having to square or cube. So if it's got an order one behavior, then it's going to win. But I don't know how Atom works. That it would be nice to compare them. I have heard that it's got some kind of second order, momentum, sort of, it's like some kind of estimate of local curvature that it uses to speed things up. But I don't know anything about it. I
It,
haven't.
Yeah, I think it's kind of what I had read is it's not really theoretically based, but it has the effect of the same thing of doing that normalization to scale the different dimensions
Is it
equivalently.
momentum that Ted described? Because that did that, right? You notice that you're flat and you go faster. That would
Yeah,
No,
affect.
it's both things. So it's the scaling by the variance and its momentum.
Okay.
So it's the RMS prop, the variance scaling to approximate what you hope is the second derivative.
Mhm.
Okay. Um, so one thing to note, Roger, is um, even if we don't do something terrible like an n cubed or an n squared cost calculation on our parameter matrix, okay, even if we do something relatively cheap, it does involve this idea of having um, um, I'm not I'm not coming up with the words well, but what I'm what I'm trying to get to is that when you start training these really big models, the parameters are spread across multiple GPUs on multiple nodes.
Okay.
Okay. And so in the small scenario where I'm training on one GPU or just like an H100 cluster of 8 nodes that have super fast communication between them, if during an optimizer step I need to do any operation, even if like I just wanted the average, the mean of all parameters, okay, that requires some kind of heavy communication because stuff is spread out. So you
Hmm.
can imagine now when you're training these extremely large models, uh, the potential downside of Muon is that you're having to you're having to send information across slower, uh, bandwidth channels in order to do your optimizer updates.
Hmm.
So what appears to be the case for like the stuff that they did with Kimi is they showed that whatever that cost is, let's say it costs you 3% more, to do each step, uh, that the speed up of Muon more than made up for
Hmm.
the fact that it's more expensive because it's not just you add some extra calculations compared to Atom. Those calculations in terms of wall clock time, I think get more expensive the more you're spreading things out across GPUs, which
Hmm.
requires slower, you know,
For
channels
Adam.
to talk to them.
Yeah.
Whereas Atom is working just per parameter wise, calculating the variance and dividing by that.
That
And
would be
so
the
it's
opposite though. What I read is that the performance gain of muon is less for small models and increases with larger models.
yes, no, what I'm saying is the wall clock time of Muon grows with larger models because your communication channels get slower,
Okay.
relatively speaking. The good news is that the benefit of using it grew, so it more than made up for the fact that it is communication wise more expensive.
Yeah.
Right? If you're doing it all on one GPU and it costs you 1 microsecond to calculate, this thing with two different parameters, right? But as soon as you spread it out to I've got 100,000 GPUs running this in my cluster, right? At some point it's going to cost you, a millisecond to get the data from this end to that end or whatever,
Yeah.
right? That's that's the dilemma with something. I think that's one of the reasons why an idea like Muon hasn't necessarily been adopted sooner
Hmm.
is because it involves this calculation across parameters. I hope that helps.
Okay. All right. Keep an eye on time then. So I actually went down a rat hole for quite a while on muon. I didn't. So this
This is a
hour is
great
kind of
paper to do that.
following.
So
Yes,
I
exactly.
appreciate this discussion. This one's was super good.
So we're falling behind though, and also unfortunately I can't just I'm not going to be accessible next week, so I can't just stretch this out. So I think what I'm going to do is just pick up the pace a bit, and we'll try to get through. So um, uh, this was one that, again, I need to go back and figure out. They said the overhead is related to TM over B, where M is the model dimension, which typically means the dimension of the hidden state, but maybe they're meaning actually the parameter dimensions, batch size, and number of integration steps. Um, so that would make sense. Newton Schultz would go over that. Basically, just it's a efficient, iterative way of approximating this inverse of a matrix, doing inversion. Okay, so muon clip. So what they found is that uh, they had this instability with muon at scale. Like the original paper didn't go up. I think maybe it went up to 1B or something like that. So it hadn't been tested up to these larger scales. But what they found is that with muon you have this tendency for the attention. Um, so when you do a query times key multiplication is that's right down here. Query times key multiplication. You scale it by dimensionality and multiply it times the value. That's how the softmax attention works. And what was happening is this value was getting to be large. Now softmax always will normalize it down. So I think it's a probability. So the area under the curve is 1. But you were having really big numbers in the middle, and that was creating numerical instabilities. They had a theory as to why that was happening that they introduced that it just had to do with the fact that typically with Atom, I guess it's a very sparse update, whereas here they're doing an update to all of the parameters in a scaled way, and so it was more likely to explode. They said. So what they did is they just came up with, to me, seems like a super simple algorithm, like overly simple, and they just do a hard clip, but they don't do a clip on the queue or the query or the key. They do a clip on their product. So the logits into the softmax, max logic per head scalar. So they're scaling each head so that they limit the size of this product, the maximum logic size, and I guess I didn't notice this before. They say in this batch, so it's possible they update this for each batch. They adjust the scaling, and they do it per attention head. And there was one thing I didn't recall this. They talk about head-specific query key components, but then they also have these rotaries. So my recollection is with rope encoding, this architecture, by the way, is supposed to be similar to DeepSeek v3 with a few tweaks on the parameters, I think.
My understanding is the architecture is identical to DeepSeek v3, like the outside of these adjustments that they've made with the optimizer, et cetera.
Okay, that's even closer than I thought. Okay, yeah. So yeah, we'll look at the model changes. But anyhow, so I didn't remember this, but apparently there's rotary matrices in there for the rotary encoding as well.
Yeah, that's the function of the latent attention compression that they do.
Oh, okay.
If you call multi-head latent attention, they squeeze the keys and values into a smaller dimension, and that reduces the size of the KV cache. They eventually end up expanding them to do the QK dot product, but they're expanding them in sort of a virtual way because they fuse the expansion with the next matrix multiply so that it's not really more expensive. But the bottom line is that when they shrunk the keys, they didn't want the keys to be rotated, which would cause the same words to be different. They wanted to compress the unrotated keys so they would compress nicely and then just use the rotation separately.
Okay, that makes sense. And so that's why these guys, they are scaling differently than, so the rotation part, it's shared. So shared rotary is being left alone. They're scaling mostly the query and the key.
Yeah, and intuitively that makes sense because what that's supposed to do is you're supposed to be able to see if it's 1 token to go, 2 tokens to go, 5 tokens to go, and at some point it gets to many and it's hard to tell exactly how far away it is. But you don't want to mess with that calculation, and also there's probably no need to because you can't get unusually large values because you know that you calculated them based on this rotation matrix and that it's like sort of like this norm 1 thing.
Yep. Okay, and this is the algorithm then that they use. This looks a lot like, I think, well, it's almost identical to the muon one, except it looks like this term, I think they added a weight decay term into it. That again is helping to bring those weights down to a smaller RMS. And this is where they implement this QK. So I understand why QK, because it's the product, the clipping in the QK space, and they're looks like they're calculating it on each iteration. they find the max and then scale it based on that. So this is the result. So on the left-hand side over here is the magnitude of this max logic. So that's the biggest QK uh, logic that's going into the softmax, and it grows. This is reminiscent of the discussion we had, Ted, about on the residual stream, that it just kept getting louder and louder and louder. It seems like that's kind of similar type of thing where you want more attention, and there's nothing kind of pulling it back. So you get this growing magnitude of the QK. On the right-hand side is when they've introduced their clipping. So it's kind of interesting. So in the beginning, it's growing, growing, growing. I don't know if the scales are, no, the scales are different. This is 100. This is 1200. So growing, growing, growing. They clip it at 100. And so now they're keeping those scales down. And eventually the system starts to come down from that. So my guess is it's that weight decay term that is then pulling that back down to a smaller value, and it levels out. So that's their kind of results of that's the rationale and the results of their muon clip. Any other questions on that? Okay. All right, so then we move on to some of the training stuff. So again, they talk about synthetic data used during generation. This is an interesting thing where they talk about design rephrasing. So they're going through apparently in their data, and they're taking their input data, the training, and they're using, I think, the Kimi 1.5 model to rephrase the training data basically. And so it's prompted to do these types of rephrasing. They also have something where a little trick where if it's a long data set, or not data set, but data example, they don't just rephrase the whole thing. They broke it into chunks to do the rephrasing, a little bit of trick. And then I think we perform fidelity checks to compare semantic alignment of each rephrased passage with its source. And again, I think a language model is doing this. So it's interesting. I still haven't got my head around what it means, what synthetic data really means when you're using a model to generate model from the original data. I kind of, in my mental model, Julius is kind of using this idea that the original data is very noisy, and so I have to have lots of it to kind of normalize out the noise. Whereas this regurgitated data is already been passed through a filtering. It's in the sense that it trained a model, and so it's a less noisy signal to have to deal with it. I don't know if anybody else has intuition on what it means to work with synthetic data.
So Roger, in brief, in vision applications, it's common for us to run hundreds or even thousands of epochs on the same training data because images are continuous and we apply all sorts of crazy augmentations. We do crops, we do rotations, we do color jitter, and this prevents overfitting, which would happen if you just use the images unaltered over and over again.
Right. So it's kind of a different form of synthetic data. Yeah.
Up till now, people haven't had good augmentations for text.
Mm-hmm.
Okay. So hypothetically, you could say, when you see the word good, I'll replace it with the word great. And that's an augmentation you could do. But what if in some sentence, the word good is actually not being used that way? It's being used a different way, right? You know what I'm saying? So this is their way of devising an augmentation for text that actually doesn't catastrophically break things, especially for scientific things. Heaven forbid you have some math thing, you change a word, and now you've taken something that's like true to something that's false, right?
Yeah. Yep.
So then what they do is they do this paraphrasing thing with a reasonably powerful LLM, Kimi K15, and they hope that paraphrasing is reasonably accurate. And then as a sanity check, they had that check at the very end.
Yeah.
So It's kind of
I
interesting
think I
though.
still, go ahead.
Oh, sorry. I was just going to say in this table, they show that, like, hey, you can do this. You can use the data 10 times with these paraphrases and you don't get overfitting. You actually get better performance. But then in the body of the text, it says basically they only did it twice. They were still very conservative about this augmentation.
They only did it twice. Where does it say they only did it twice?
Uh, it, yeah, that last sentence
And
there.
each corpora is rephrased at most. Oh, huh. I didn't notice that. I picked up on these 10x ones. I didn't realize that. So they found the trend was solid, but then they were conservative and didn't even do it. I think, Ted, I think my problem with I had the same problem that I had with uh, some of the augmentations they do in image, like where they're doing a rotation, for instance, as an augmentation, is like, why don't we just rotate the filters that are generated from the single rather than rotating the original? And I kind of feel like there's a similar issue here where it's like I'm using a language model to do the augmentation. So why can't I just pick up on whatever signal that language model already figured out and use that as part of the training? But it seems to work. Just augmentation works, and this seems to work as well. So
Yeah, I think you've got a point that might work. This, by the way, can be done as a pre-processing step completely in parallel, so it is somewhat convenient.
yeah, it's convenient and it's also reusable too. Once you generate the better data set, now you got it around, you can use it for
Right.
training
So
other
basically,
models.
you start with Wikipedia, and then they basically have Wikipedia paraphrase copy number one, and had they wanted to, copy number two, copy number three, where it's the same content, it's just been
Yeah,
paraphrased.
yeah, yeah. So okay, then this was getting into the architecture itself. Uh, Warren, thank you for clarifying. So it's actually identical. You said architecture. They've changed some things. I know they increased the number of experts, um, and they decreased the number of attention heads. This was the comparison of kind of what parameters went up, what parameters went down. Um, I wasn't quite sure what the expert grouping was. I tried to find that. Anybody know that one?
That's where you try to co-locate experts on the same GPU.
Oh, okay. Okay.
Um,
So they didn't
so
declare
that,
that.
that hopefully gives you slightly better training performance. It doesn't
Gives
functionally
communication.
change what it's doing.
Gotcha. Gotcha. Okay.
Yeah, so the big thing you'll notice here is that it's more experts and fewer attention heads.
Yep,
So
exactly.
And more
wherever you,
sparsity. Yep. And more sparsity. And that's coming up in a slide in just in a second. Yeah.
yeah,
So this
that's
was
what the more experts gives you is more sparsity. So they're using 8 out of 300
yeah.
experts, which is that's a lot of experts.
Yep. Yep. Yeah, this was from the GitHub for on the I think I provided a list somewhere for the Moonshot GitHub, and it shows those parameters. Interesting, they did this sparsity scaling law. So Ted, this is where they talk about the kind of the number of experts and versus how many are active at a time. Um, Let's see, they look at for a fixed budget, increasing the total number of experts, i.e., increasing sparsity, consistently lowers both the training and validation loss, enhancing the model overall performance. They talk also about, let's see, so here's the slide. So the way I read this is we've got different sparsity levels. And my guess is, so these are different model sizes for each one of these curves. You got the training flops down here and the validation loss over there. So at sparsity 8, you have a model that's trained, um, this size model that's trained and it reaches the optimal point along here. The same model with same sparsity, and this is going to be a little bit larger. You get a better loss, but it follows these curves. And the key thing is to see that the sparsity 8, the loss curve is up here, whereas sparsity 64 is this one right down along the bottom. So sparsity actually got better as you increased it. And they chose, I think there was some other offsetting factor, but anyhow, they ended up choosing 48 as the sparsity. So 8 times 48 is whatever that number was, 380 or something.
Yeah, on my quick read, I didn't understand why they didn't do 64. Like like they showed that it just gets better and better. Obviously, it's diminishing returns, but um, I didn't. Maybe I
Yeah,
missed it. I just didn't see an actual explanation why they
I thought
picked
that
48.
I thought I did see a factor that something was getting more expensive. I thought they mentioned that in the paper, but I couldn't repeat it right now.
Yeah, I
But
mean, your model's getting bigger. You know.
yeah,
I
yeah.
think what the or from my understanding, I just posted in the chat there. There's a little diagram of the difference between Kimi and DeepSeek
Oh,
architecture.
nice.
Another little blog, but the sort of general feeling that I got when reading about what they were doing with the architecture was let's take DeepSeek because we know it works, and then let's change as few things as possible to only the direction that we like decide to change them. Just because we don't we want to like take a like if it's not broke, don't fix it, and then like we want to know why this is getting better if it's getting better sort of outlook. So they were sort of starting from the constraints of DeepSeek v3 and change as little as possible. Since what we're doing is switching out the entire optimizer, we want to sort of like isolate that as our kind of control variable. Is sort of my understanding.
And it did seem to be kind of a data-driven approach, right? Where they did this. I like the scaling law. So they did small models first to see what the trends are before they started running the bigger models.
Yeah, the constraint number one, inherit DeepSeek v3's architecture wholesale and then tune only the structural hyperparameters is something that's coming from that.
So
That's
when
a
the
nice slide. I'd like to go through that. I'm gonna roll past it right now just because we're low on time, but it looks really good.
a quick question, when it goes back up, is that overfitting? In other words,
Uh,
increase the
I
flops and it gets worse.
I think it
I
would
think
be.
they haven't explained this diagram, but this is one of those Kaplan chinchilla scaling law things where if you do like ISO flop, I think, then when you make part of the model bigger, then that forces you to do less training or whatever in order for it to be ISO flop. You know what I'm saying?
Mhm.
So like at
The compute
the
optimal, looking for the
yeah.
compute optimal frontier. It's that little
Yeah.
elbow in the curve. Yeah, I
So
see.
those curves are based on compute optimal, not based on lowest loss or perplexity,
Mhm. Okay.
if that makes sense. So I don't think they've sufficiently explained it. But if you go back and you look at the curves in Kaplan or Chinchilla, then you'll see they look like this. And the bigger models always do better, but they don't. If they do 10% better but cost 20% compute, they look worse in the compute
Mhm.
versus val loss curve.
And the other quick question I had is, well, it doesn't have to be quick, but it should be quick, I guess, and that is, how much fundamental difference is there between, let's say, 8 experts and 8 attention heads? In other words, what I guess it's just in how they get combined, right? Because in both cases, you've sort of, and it's also a different partitioning of the space. But it just seems like a mix. It seems like a set of tension heads is a kind of mixture of experts. Each attention head is its own expert. It gets to do what it wants, and then you combine them.
That's an
Yeah,
interesting way
so
to
they
think of
they
it. Yeah.
tuned they tuned the number of attention heads. I think my short answer is that conventional wisdom is that those two are fairly orthogonal. You have to have both components, but once you have a certain minimum of them, then basically you can tune attention heads independently of tuning the MLPs.
Yeah, that's what I was going to say. Isn't the MLPs are part of the experts? They're not part of the attention heads. So you could have a large number of attention heads, um, and that equals the number of experts times the number of attention heads. But you need to also have partitioned your MLP space into the experts. Does that make
Yeah,
sense,
so
Julius?
the TLDR of that diagram Warren shared in the chat is the biggest changes they made was more experts and fewer attention heads.
Mm-hmm.
Yeah. Yeah.
Yeah, the logic behind that was I just saw it. Cutting edge halves the quadratic term, which is a huge win for long sequences, and they're trying to make like a primarily agentic plus coding model, which all like very the primary use cases for that are always going to be multi-turn, and they're always going to be long context, so they wanted to optimize for that.
Mm-hmm.
It's a great graphics. Thanks for sharing that, Warren.
Yeah, no kidding. I dropped a link in the Slack to the guy's blog, but it's a very good blog post on Kimi as well.
Okay. Okay. All
Thanks.
right. Yeah, let's keep going then. Number of attention heads. So yeah, they talk about reducing the Warren, you already kind of summarized that. It ain't okay, so the increase in the number of attentions from 64 to 128 while keeping the total expert count fixed leads to 83% increase in inference flops at 128K sequence length. So, and I think in here we'll see that. So this is the models, um, the Kimi models, and these are the double attention. So that it'd be the DeepSeek model. There's a small gain in validation loss, um, but they didn't think it was justified. I did notice, I'm guessing that this is supposed to be orange, purple, green, or excuse me, blue, purple, green, orange. It seems to be reversed. I don't think
Oh
that,
yeah, that does look funny.
yeah,
Yeah.
it looks like they got that backwards or got a mistake there, but
The main thing though is you're supposed to be comparing the squares to the circles, and they say the circles are slightly better, but at quite a cost. So
exactly. Yeah, that 80% cost for that. So that's why they chose to reduce that. So. Okay, training infrastructure. We've seen this type of thing before when we were looking through the DeepSeek paper where they're trying to overlap. I did notice that I remember dual pipe, they kind of traded off memory, GPU size. In dual pipe, they had the inference going kind of both directions, and it traded off increased memory for higher throughput GPU utilization, I think it was fewer bubbles. In this case, they decided not to do that because it was too high a cost of memory. But these ones, I'm not going to go through the details of them exactly, but it's the same type of, here we got the attention calculation, here's the MLP calculation. This is I think it's the distribute and collect for the expert parallelism. Similar type of thing. This is during the steady state stuff where they're overlapping computation and communication. This offload onload is kind of cool. There's a place where they talk about, okay, so here's the architecture. I don't know if they talked about the full size, but they did say that you can do it on anything. The way they set up the training, any number of 32 nodes in the cluster, the same algorithm works. And that was important, I guess, because when they ran these different tests, multiple tests, sometimes it was small, sometimes it was large. They wanted to use exactly the same scheduling and everything. Here was some of the training details that I pulled out. So pipeline parallelism, expert parallelism, we saw that. Again, we covered that, and 0-1 data parallelism. We saw all that in a review on DeepSeek. They did use the 1F, 1B scheduling instead of the dual pipe. And there was something where they said the expert parallelism, they had to reduce down to 16 because using the smaller number of heads, it was like they needed to balance the communication and the computation. So in order to do that, they ran the parallelism down to 16. They did some recalculation to optimize it, things like the nonlinearity layer norms and the projections in the latent attention. Some storage in FP8. Oh, this was the one that I thought was kind of interesting. So activation CPU offloading. So they have a bunch of the activations that they offload to CPU. And because you can, you get storing those around can be expensive, use a lot of memory. So they just actually offload it. And as long as they can overlap it right, offloading and onloading of that communication can overlap. So it's moved off when it's not needed and it's brought back before it's needed again. As long as it's 100% overlapped, they can make that work and make the more efficient use of the GPU. That was kind of cool, I thought. There was another thing I noticed here that, okay, so this is the learning schedule for the first 10 terabytes, tera tokens. They used a fixed learning rate after a warm-up period. Yeah, they had a warm-up. And then they did a cosine decay rather. What's that, about an order of magnitude cosine decay? And I think we'll see, I'm guessing, so that's it, the 10 out of 15 tera tokens where they did that. Batch size. Oh yeah, they trained out to the very end. They trained 4 sequence, then 4K sequence length, and then they went to a 32K sequence length, so they got larger. And then finally, they used the yarn method. So did I put in a slide about, yeah, yarn? I'd heard this a number of times, didn't know exactly what it was, but it's basically this idea with rope, you can train at one context length, and then have this algorithmic way of extending it with a little bit of fine tuning after you've modified the rope embedding. And yarn, the key thing is it doesn't scale the frequencies equally. It scales high frequencies less and low frequencies more. So it helps to improve the high frequency information. So that makes sense. That it seems like we had that discussion before. It seems like the rope encoding is important for what's very local. And as you look out over longer horizons, it tends to be less important. And then so yarn's kind of leveraging that if that's an insight, that seems to be leveraging that same thing. So here's the loss curve, and I guess this is an impressive loss curve because it ran the whole way without having any explosions on this, and they're attributing that to the muon clip, QK clipping algorithm. That's introducing the stability that allows you to follow that curve. I'm wondering if this little curve here is related to when they started changing the learning rate. Because it occurs about, I didn't understand what that little kink in the curve was, but it happens to correlate with about that 10 trillion token mark. So maybe.
Yeah, that makes sense. The learning rate was probably a little too high at that point.
Yeah.
And then when the cosine kicked in, it helped.
Yeah, you'd almost think in hindsight it might have been better to kind of kick it in a little bit earlier. But anyhow, so this was post-training. And I think what I'm going to do is I'll shoot, so we'll try to get this done in 15 minutes or so. So we'll run 10 minutes over or so, but not much more than that. So if everybody's okay with that. All right, so tool use is important, and they're training it at its core. They're training it for tool use, and this is the way that they did it. And I forget, I didn't copy the number, I think, but I think they ended up with something like 20,000 tools that they created. And I still don't quite understand how you can create a synthetic tool. But they apparently so they do the spec generation, assuming with a large language model, and then they define the agent, And then they have something that's another, again, I'm assuming large language model that's doing the trajectory generation, like was the tool used effectively. This was the picture that they had. So this one, I think they said that they scanned GitHub. They got 3,000 MCP tools definitions there. So they pulled those in as part of it. And then this is the synthesized tool spec. So they dreamed up a bunch of tools. And I think it was the large language model, I'm guessing Kimi 1.5, that they used to generate these tools. And then they had generated agents from all those descriptions. The rubrics was apparently an important part where they were using, so rubrics, look that up. It's basically that you're doing a multi-dimensional measurement of performance. So instead of just kind of a ranking performance number, you say, okay, how did it compare on task following? How did it compare on fidelity? Whatever. So there's a number of dimensions that they define that the agent that was measuring it was judged against. So I think then this model is saying the way we generate those is we'll come up with a task that we made up, we'll give it to the agent. It'll use one of these MCP agents and the tool simulator. Now here's where I get lost. I don't know how you can simulate the tool that you synthesized, but somehow in here they're doing something along those lines. And then this judge, another language model that was trained to judge, will use the rubrics, the dimensions of the quality metric to decide what was the performance against that. Interesting thing about this then is that, let's see if I have the rubrics. Yeah, 20,000 synthetic tools, 3,000 real tools. And this was interesting. So what they're basically saying is, hey, we understand that synthetic tools could diverge, but we want the language model to learn to work with large variety, a good distribution of tools. And so what's important is that we're coming up with this distribution. We're making a lot of different high diversity of tools that it learns to work with. That could drift off into, it's fully synthetic, so it could drift off into some place that doesn't make sense. But we've got 3,000 real world examples that we can use to kind of ground that model. And so it's interesting, this idea that this mixing of the synthetic with the real world allows you to get increased diversity than what the real world would give you, but the real world ones still keep it grounded. So in learning all these different tools, it's now, whether or not these 20,000 match exactly what tools this model Kimi is going to be exposed to in the real world, we don't know, but it's been exposed to a high diversity of tools, and so it's learned how to work with different types of tools. That was my take on it. Yep. Anybody or any comments on that? Okay. Okay, and then reinforcement learning being the last one, I think, where they're basically it's believed to have better token efficiency and generalization than supervised fine-tuning. I don't know. I guess I don't know where they come up with that for a definitive, but that's their general belief. And so their experience with earlier models, they're going to increase the RL. They created some sort of gem-like, so this is OpenAI, I think, created an interface that was a standard interface that a model could use to interact with the environment. It's kind of, give me an observation, I'll give you an action, you give me the result, a reward, and give me the new observation. That's kind of the sequence, the API. They have something like that. They don't go into any details, but they created something internally. These are probably pretty easy to create, just worlds. Although in the language space, I don't know. This would have to be a gem-like thing in the language space, so I'm not exactly sure what that looks like, but it's going to be the same type of thing of I try something, I get a reward, and then I try something else. Um, some of them, yeah, okay. So some of these, a bunch of math ones, for instance, um, you can know definitively the answer. And so they have, I think, some specific domain specific um, systems that will provide a truth-based reward. And then they have other ones where they have a critic that measures it. And someplace they talk about using just a language model that's been trained on. I think they had one that's trained on critic. I forget what the other ones are, but Rubik's, I think, might have been one. So this idea is kind of interesting that they did say that the critic used the same language or same model. So it was, on the one hand, generating the response, and then on the other hand, it was critiquing its response. And somehow this, in an RL context, kept improving the model. And it's my only intuition can be that judging, being a critic is easier than being the generator. And so the model doesn't have to be as good to critique something from a better model. And that combination allows the model to continue to improve. There's a couple things that they had in here. Generates response, blah, 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 blah. Critic ranks based on the core rubrics, which I think they define. Aim to, yeah. Yeah, I think I'm not going to provide any more detail on that, insight in that. Does anybody else have any? I thought this was really cool. So this is the idea. This is the kind of a model, the teacher student, where the student actually gets better than the teacher type of scenario. You let this run long enough and the model just gets bigger and bigger, or better and better, as long as you can keep it grounded so it doesn't drift too far off. Any other questions, comments? Okay. RL algorithm they used was fairly straightforward. I think this is, so they're subtracting the mean reward. So the critic's providing the reward. I think they're subtracting the mean, which means this is an advantage. And then they put in this term, which I think is going to be basically the KL divergence. So they're trying to keep it so that the model doesn't drift too far off, and providing a loss signal that's an advantage signal from the critic. This was kind of interesting. So they just engineering. Go ahead, Ted. Oh,
I was just going to say, this is a KL penalty, but if you read the K1.5 paper, I haven't fully wrapped my head around it. But the bottom in like other papers you see, it's the policy base from before they started RL training. And if you look here, you can see it's pi old, which just means last step.
yeah, that's what, okay.
So in that sense, this is a very different algorithm from GRPO, and I haven't even looked at the new GRSO algorithm.
Okay. GRPO used it, they used a prior as well, right?
No, I thought it was
no, they used
it
it
was
on
base.
yeah, that's right. That's right.
The prior is used to calculate the advantage.
Yeah. Okay. So if this isn't GRPO, that's another area that they diverge then, right? DeepSeek used GRPO, didn't they?
Yeah, but I think Warren was talking about sort of the model architecture, not the training.
Yeah. Okay.
Yeah, exactly. Yeah, you got it.
Okay. And then here, I thought this is a neat little engineering issue, is they have some of these rollouts will take longer when you're interacting with the agent. Some you might get to a solution quicker. So they did some scheduling here where If you got one of your samples is running too long and the others have finished, then you just kind of pause that and restart it, run it with the next batch. So kind of dynamic batching type of thing going on. And this is the gym that they have, like OpenAI gym. Another one was widely observed that RL often results in substantially increased length of model responses. Yeah, I can see that. And what they imposed a maximum token budget and a penalty if it thought too long. So as a way to kind of provide a signal. This seems a little, I don't know. It's like a hard stop on it. I'm surprised they don't just add some sort of cost per token type of thing rather than a maximum, but so be it. Performance looks good. Everything's good. There's some places, so this is Opus 4 on SWE Bench. It's not doing as good. One of the things that is a theme when they're looking through their results is that they claim to have like a leadership state of the art in the open software. We don't want to confuse that with the proprietary. So like in these cases, so the notation is bold means I'm actually leader against all the models, open and closed. Bold underline means that I'm leader amongst the open source, but not if against the proprietary. So a lot of these, you can see that it's yeah, okay, it's got leadership in the open source space, but we're still falling behind, some to different degrees. Here's one 29 to 18. So some places it's falling substantially behind the closed systems. Tool use, I thought it was kind of interesting that these guys, not surprising it's leader against the open source, but it's since it was trained specifically on tool use, kind of surprised it didn't have it. Well, I guess here's one, telecom, Tau2 telecom. It's across the board leader, but on the other ones, it's still behind, like Claude. And yeah, that's a pretty big difference too for Claude. Here's a place where they do well. So math and STEM, maybe this is related to the fact that the math RL training they were able to have, well-founded RL feedback. They knew what the ground truth was, and easy to measure. Here they're kind of mostly state of the art against all models. So that's kind of impressive. And again, more. So strong leadership position in the open source space, still lagging a little bit behind some of the proprietary models. Okay, so Kimi K2, 1 terabyte. This is what they viewed as important. Token efficient muon clip optimizer. Again, it seems like somebody had said heavy lifting done by muon. I kind of feel that way, but they've added this little tweak to it. And then this pros training using unified RL for both verifiable and self-critic feedbacks. Okay, they also Moonshot they have a GitHub, and they're more than just the Kimi. They also there's a coding agent, and I didn't quite understand this because they talked about Kimi K2 does not have vision, that they're going to be doing that, I think later this year, they said. But there is a Kimi Vision version. I guess that's maybe a smaller, earlier model that's available. On the dev side, the claim here is that for a smaller model, it looks like these are mostly open source, they have a leadership position in the performance for the SWE bench. So good position there. And then hands-on, I think we'll just skip for tonight. I was going to jump in, but if you want to try it, let's see, where is
the moonshot.ai is their hosted version, and then OpenRouter also has one, I believe.
I thought they did it, Kimi.com too, I think. Kimi.com, I'll pull it up.
Oh, I guess so. Cool.
Yeah, you can sign up for it. Pretty easy and play. One of the commenters I saw made the comment that it's kind of slow relative to some of the other ones, and a response from Moonshot was it's a matter of scale. This thing's really taken off, and we can only service so many. So I wouldn't see any reason that would be architecturally slower, but right now the experience that you'll have would be slow. And then the one other thing, if you're, oh yeah, this was the SWE bench. Where is Moonshot on there? They're actually not on there. Huh. This was the one other blog deriving muon, Jeremy Bernstein. This was the one I found late, but it seemed like it was starting to provide some theoretical foundation for muon. So I'd like to go back and finish that. And Julius, if you're still around, that might be a point for you as well.
Yeah, I've got that on my tab already. Thank you.
Okay, great. All right, and I think that was it. So sorry for running a little bit over. But there we are. We got it done.
Nice work. Appreciate it.
All right.
It's great. Thanks, Roger.
Yeah, thanks a lot.
All good. All right, I'll stop the recording.